Hi everyone, my name is Liu Zhongxi and here it is my paper reading. This is the article about quantitation of malaria parasite-to-erythrocyte cell-to-cell interaction using optical tweezers. And the major author is Alex J. Crick. And here I'm going to talk about the background of optical tweezers and the invasion of malaria parasite to erythrocyte. Here I'm going to talk about the optical tweezers. And the optical tweezers, also called the single beam gradient force 3D optical trap. And it is using the principle of radiation pressure of light and the action and the reaction force. And in this picture, this is a beam, and this is a particle inside the beam. Here is the intensity of these beams. We can show that the center of the beam is the biggest intensity, and this is also called the Gaussian beam. And the photon B here hit this particle and has an action force here when it came through the particle, and it will have a reactive force here. When we combine these forces together, we will have the direction of the FB, which is this. And the same thought of the FA, but the FA will become bigger because the intensity of photon A is bigger than photon B. So let's combine these forces FA and FB together. We will have the direction of this, and it has the direction of the F gradients and the direction of the F status. So these forces FA and FB will take this particle to this direction. And then let's talk about this picture. This is a lens, and its focal length is here. And this is a particle. When the beams came through the particle, and it was the same thought as this picture, the FA and FB will lead this particle to the focal length of the beams. So if we defined this axis is x-axis, and this axis is the y-axis, and this axis is the z-axis. So we can define that this is the 3D optical trap, and it will always trap the particle to the focal length of the laser beams. This is the life cycle of the malaria parasite, and this article will focus here the invasion of the merozoites. And by using optical tweezers, we can know the force of the attachment of merozoites and the erythrocyte. And here is the first result. Invasion can be induced by delivering merozoites to erythrocytes by using optical tweezers. At 0 seconds, the merozoites are not being catched by the optical tweezer. And then the author of the article delivered the merozoites by using optical tweezers to the erythrocytes, and which takes 3 seconds. Then at 20 seconds, this is the progress of the invasion. And at 80 seconds, we can clearly see that the red blood cell has been deformed. And this is called the erythrocytes echinocytosis. It has many stings here. And this result proved that by using optical tweezers, the merozoites are not being killed by the optical tweezers, and the merozoites can still invade the erythrocytes successfully. And here is the second result. Erythrocyte membrane deformation can be induced by forcibly reorienting merozoites on the erythrocyte surface. This is the merozoites, and this is a red blood cell. And by using optical tweezer to change the surface, you can see the red blood cell surface has been deformed. And it's very strong. And now the optical tweezer is off, so the deformation is not caused by the optical tweezers. So this result shows that the merozoids on the erythrocyte surface can cause the deform. And the author of this article he guessed this might increase the invasion efficiency. This is the third result. Optical tweezers can be used to measure merozoid to erythrocyte attachment force. As research before in 2008, it shows the mechanical response of the red blood cell, and the deformation of the red blood cell can be calculated into force by using these equations. The L means the cell length, just like this, and the L0 means the initial cell length, just like this. And this is the relaxed state of the cell. And then delta L is the increasing length. The force equals to the constant of cell stiffness and multiplied into delta L. And the K, the constant, is equal to 20 piconewton divided by micrometer. So let's see the fig A. There are two erythrocytes being attached by one merozoid. And then we use two separate optical tweezers to pull two erythrocytes in different directions. And when we pull off, we can calculate the maximum L. And by using these equations, we can find the force now is almost 40 piconewton divided by micrometer. This is the detachment force. And then see the fig B. This erythrocyte is being sticked on the glass. And when we're using optical tweezer to pull another erythrocyte, we can still using this delta L to find out the detachment force. So this result shows that we can using optical tweezer to measure the attachment force by measuring the cell length. And this is the fourth result. Invasion inhibitor can affect either the frequency or strength of merozoid to erythrocyte adhesion. Let's see the fig A. First, author used the optical tweezer to put merozoid to the red blood cell, and then to measure the percent of the merozoid still attached to the red blood cell. This is the fig A. And the fig B is the attachment force by using the result 3. And the first drug is heparin. Heparin is known as a very strongly block invasion at the very first stage. And if we see the percent of the merozoid attachment to the red blood cell is very few, and the attachment force is very small, which we can say that it decreases the attachment force. And then the merozoid cannot be attached to the red blood cell to block the invasion. And the second drug is cytocholine D. As fig A and fig B, we can see the percent of merozoids are almost the same as the wild type, and the detachment is almost the same as the wild type. But it can still, by disrupting the actin myosin motor to decrease the invasion of merozoid. So maybe it's not using the same way as the heparin. The third drug is enzyme treatment of erythrocyte. And when the post-aggress is in 3 minutes, the percent of merozoite is fewer than the wild type, but it's not very obviously. But when the post-aggress is bigger than 3 minutes, the percent of merozoites is very few, just as much as the heparin. And the attachment is fewer than the wild type. The other thing may be the enzyme treatment of erythrocyte is to shorten the work time of invasion. And we'll have the discussion. Merozoites can adhere to the erythrocyte membrane at random orientation with forces of almost 40 piconewton. This is from the result 3. And heparin blocked merozoite attachment to any surface. As the result 4, we can see the attachment force is very small. The cytocholine D treatment had no effect on attachment force, either positively or negatively. We can see at the result 4, the attachment force is almost the same as the wild type. And this is my paper reading. Thank you for listening.